So application windows, share.
Yep.
I've shared. Can
Yep.
you
We can see your.
can you see the
I can see it, and that's fine. And could you just go into full view at the bottom?
all right. So once I
Yeah,
go into
yeah,
full view, I won't be able to see anything else. I hope that's all right, right?
that's okay. Lovely. Yep.
Yeah.
You, that's okay. Then everyone can see. So, right, we've got the three people with us at the moment. We've just got one or two other people that are coming. So,
You let me know when it's the right time to start.
I'm just going to set off the recording, then we'll go.
Okay. So
Okay. I'd just like, first of all, to introduce you to Dr. Roy. Uh, his last name's quite a difficult name to actually pronounce, but it's Subhashis. I've known Roy for, I don't know, 10 years or so, and he is a bit of a pioneer in terms of AI automation and robotics. So this is going to be a very interesting session. Roy, I'm handing it over to you. Away you go. Thank you very much.
thank you. Thanks very much. Thanks very much, Martin. So I'm just sort of going to give a very quick overview. And the topic that we have chosen today is about automation and applications of AI in high value sectors. So the way this particular presentation is divided, it's actually divided in two segments. And the first segment is going to focus more about the overview of AI. And so we are going to just look at very introductory sort of areas into this, what AI is, trying to define that. And then we will delve into how AI has actually diffused across various high value sectors and how it's been used. So this particular webinar is more of an introductory in nature. We won't go in the depth of each of those sort of AI models, but we'll have a very broad brush overview of how they have been used. So please, if you may have any questions, I think protocol would be to raise hands. I may or may not be able to see it properly. Martin might let me know. So I'm just going to stop once if you think there is something that needs some explaining. So what sort of goals we are going to set for today's talk? It's first of all to demystify what AI is, and then we'll, as I've mentioned, go into a bird's view of AI automation and applications. And then we are also going to have a sort of a conceptual high level overview of various models and algorithms that's used in all these sectors. And the things that we would be we could progress in the future, which is out of scope, let's say, for today's presentation. It's all about building an AI solution. So if you look at it, it would be very thorough mathematical foundations, and then getting into the programming frameworks such as Python or even Java for that matter, and then actually be able to pull that up for
Okay.
designing and delivering industry specific solutions. Sorry. Hello.
Dr. Basil, could you please mute your microphone? Okay, carry on, Roy. Thank you.
All right, thank you. So, as we move into this first section, we are going to now get into the various sort of sections. So, primarily, what we are going to look into, we are going to look into the AI learning part of it, what that constitutes, what sort of generations we are looking at within AI, and then we are going to briefly touch upon what is that future that we are looking at for AI going forward. So, so I would like to sort of have this session more on an interactive basis. So we have got uh, 3 or 4 participants, and I'm going to give you a very quick scenario, and then you might just come back with your responses. So scenario one is, suppose that you're in a Jurassic world. By the way, if you're a lady here, then you have to just reverse that example. Apologies for that. So, in a Jurassic world, you've got a simple robot with you, and that robot just recognizes you, that it does. And then you train that robot with very simple instructions. So, you say, if you actually see 2 hands and 2 legs, then you can shout that, run, it's dinosaurs who are coming. And if you don't see, I mean, say 2 legs or 2 feet in a very simplistic manner, then just say catch that fish. So what it means is it's a very simple world. You're in a Jurassic world. You're either trying to go food hunting, fishing, or you're just trying to evade a threat. So now, of course, if you're a lady, then it's your boyfriend or husband, whoever. And then if you're a guy, then your girlfriend arrives. And then what do you think that what would this robot shout? Would you be able to give me a quick response? Anyone?
Run, dinosaur is coming.
Dinosaur is coming. That's right. Yeah, that's the answer. So thanks, Eunice. And so that's what we are looking at. So essentially, what I wanted to emphasize here is when you train data, it's the data that is actually drive that model. But we have pinpointed a very important principle about this. So let's go into scenario two. So hold on to your thoughts for the scenario one. And scenario two, there's a slight spell error here. I was quite tired last night trying to get all the slides together, so I met a few issues. So it's beer, it's not beer, a bear here. So essentially, there's a convenience store, and then we and this person who runs this convenience store observes that every single Wednesday, when guys come in to shop, they obviously take a bottle of can of beer or whatever they want to buy, and they also buy diapers. So he observed this trend persistently, and then he realized that it's best to keep these two products together so that there is customers are going to be able to um, have the best offers available as well. So his sales increased. That's what he did. So, question: what could be behind all this? Anyone? This is a trick question, though. Just say. So let me give you a quick response on this because the answer is really tricky. I know about it because I constructed it. So essentially, these ladies in that particular local area, they had some sort of Wednesday, tea party, and the husbands had to really mind children. So that's the kind of fetch around it. So they bought beer, and of course, they bought the diapers. So on from here to say scenario three. Um, so again, you're dealing with very similar robot, but now you're in present day world, and you're trying to train this robot. And what you do is you give him anything that is spherical in nature and ask him to put it on the left hand side. And if you give him something squarish, a box kind of stuff, then the robot should just put it on the right side. Question, um, primarily what this robot has learned in the process and what will happen, let's say, when we give a new object, and if that's square in nature, what do you think will happen? And if it's a spherical nature object, what do you think will happen? So anyone, it's quite straightforward, but just in case, if you want anyone to answer here. Uh, okay, I'm just going to quickly get into this answer. The answer is quite straightforward. If you give a spherical sort of ball nature of the object, this robot is already trained. It is going to go and put it in the left-hand side. And if it's a squarish object, then it's going to go and put that out in the right-hand side. So these three scenarios, with this, you actually have got already the basic building blocks of what AI learning is all about. And so when we spoke about this robot who was trying to put things together of similar nature, we were looking at something called clustering algorithm. So it comes under unsupervised learning. So unsupervised learning is when the machine is given some sort of clue, but then it tries to organize things and structure things of its own. So that's the first part, a critical part of AI building block. And there's another type of unsupervised learning, which is association rule. And that's about this little joke we had about when somebody comes on board, what do we do with them? This corner shop guy. So corner shop guy could look at multiple transactions in his shop. Of course, he was observant. And then he could associate that both the products, beer and the diapers, are selling, although it's very awkward. I mean, you wouldn't discover that by extrapolating intuitively. So you would definitely need some sort of ground rule, ground observation on it, and that's what actually enabled this discovery. So association rule is also a kind of unsupervised learning which enables discovery of data. So with this and the third example, if you may recall, we had already talked about this dinosaur. Come, it's dinosaur. It is got confused. The machine got confused because we were speaking about something called as training data, and that training data was passing through any of the models, and that's part of supervised learning. So when you have lots of training data and you supervise that machine, which is artificially intelligent, and then you can give it any model. It could be, for example, a decision tree model, or it could be a artificial neural network. In both cases, it's going to look at that training data and then come out of with that premise. It's going to try to classify what it can. So this is a very important point to recognize. And in terms of what we classify, again, would depend on the algorithm. On the right side, you've got a very sort of a simplistic decision tree, which is a classification model. And all it is trying to do is saying if your age is over than 40 and then you still eat fast food, then probably you're unfit. But if not so, if you're under 40 and even if you eat junk food, it's going to be all okay. By the way, I can't live without junk food. I don't know about how about rest of you. So it doesn't apply to me. But then this decision tree model just came up. So it's just a quick understanding of how trees are grown out of data. So again, if you will train this data, it is going to arrive at some sort of conclusion based on the model that you are going to run inside that AI machine. So that's the broad base. You've got either a unsupervised learning or a supervised learning, and then you proceed with rest of the inference part. Is that kind of getting into the groovy stuff that you like? Okay, hope everyone is enjoying it. Um, so let's have a quick look at what would, expanding further, what would these artificial neural networks look like and how would they actually perform? So when you think about an artificial neural network, we think it's some sort of, black box. And actually it is a black box. And in terms of explainability of the model, people don't exactly know why does it behave like that. But what is really convenient if you throw a problem through a number of inputs to this black box called artificial neural network, then at some point through its mechanism, it tries to identify. And if you give it enough sufficient training and label what you need that to happen. For example, we can label that if you have got two legs and two hands, but if that person is not very tall, if that living thing is not very tall, then that's human. So if you keep prompting, if you keep the label part of it correct, and if you let the artificial neural network know, then artificial neural network will automatically adjust and try to produce those results. So once again, the way these machines are going to learn, they're simply going to look at the training data, and within artificial neural network, it tries to mimic brain in some way, not entirely, but I'll point out where it doesn't, where it differs. But what it tries to do, it tries to get input signals. If you can see here, x1, x2, x3, and xn, they're all input signals that's going into a neuron cell, pretty much like our brain cell. And then within that, all it does is it multiplies those values, x1 times weight. It has got some weights inside. In human brains, cells also, we have got some weights. They are done differently. The mechanism is different, not electronic. But using those weights, the signals either amplify, you multiply those by the weights, or you downgrade them. When you multiply them with those weights, and at the end of it, if you have got, let's say, 10 signal inputs, you add them up, and there is something called, the sigma is showing you that we need to add them up. And after that's added, it goes into another function. The function is simply, if then else check sort of into this cell. What it does is simply checks if that value has just increased certain threshold, then it says, okay, I'm happy. So it sends a signal out to the next neuron in the layer. And if it thinks that value is below a certain point of it, value could be any arbitrary value. We'll look into that later, but can be any arbitrary value that it adapts to learn. And then based on that, if it says, say the value is 10, just for the sake of discussion. So if it is less than 10, it's not going to fire. If it is more than 10, it's going to fire. By the way, artificial neural networks are far more complex than this, but this is just a conceptual framework that we are trying to build. And then when it reaches, and there are lots of artificial neural neurons that you build in a layer as network layer. And when it reaches towards the end of that propagation, and you say, yeah, this was correct, then it does nothing. But if you say, no, this was not correct, then it does something called backpropagation. Backpropagation is going back into sort of the same cells and say, look, it was not right. We need to adjust these weights. So the next time when we are going to see the same symbol, our output should be this. So this backpropagation is the that mystery thing that is driving this entire artificial neural network and individual neurons. Does it happen in the brain cells? Can anyone give me a quick view? Eunice, you might have some view on that.
Yes, yes. I say yes.
You say yes, okay.
Yeah.
The that's okay. So it is an area of activity of research, but most likely it doesn't happen. So backpropagation doesn't happen in brain cells. So brain network is yet quite a mystery to us. We probably have not got on to that point where we fully understand. So sort of when you reconnect to this artificial neural networks, you understand we have created a simplified model, and things that we have introduced may or may not happen in brain. So our network is still going to be relatively inferior to what our brain is. Our brain is far more superior. I mean, the most superior engineered artificial neural network, natural neural network, that is.
Can I argue on that one?
Beg your pardon?
Can I argue the yes and no? Why I say yes just now?
No, no. So answer is no here.
No, no. What
So
I'm saying is that
answer.
I thought it was gonna be yes, and I have
Mhm,
on my own thought. So,
mhm.
but if the answer is definitely no, then it's okay. But is there any possibility that it could be yes because of the back
Research is
propagation?
ongoing. So
Yeah,
some researchers suspect, because brain is so complex, they
exactly.
suspect maybe there is some back
Yeah,
propagation that
yeah.
is happening.
Okay,
So jury is still out there, but present understanding is brain doesn't work like that. So
okay.
that's the present understanding. But brain does all the things that you've seen so far, minus the
Yeah,
propagation. So would have still the signals coming through. You still would have a threshold which it just jumps. They're done with a mechanism of protons, not with, of course,
okay.
not like this. And they are far more complex. But then the mechanism is still same. But back propagation is not yet been found as a concrete evidence. So that's the part. Okay. So great. And of course, the questions are for everybody in the chat here. So it's not just one person. So please feel free to interact. So now we move on to the next part. We are going to delve into this part very soon. But what I would like you to sort of contemplate or imagine is that artificial neural networks can be of various types. And some of the things that you've heard mostly is called deep learning neural networks, deep learning models. They are actually artificial neural networks. They are laid out with multiple layers, not just one or two, but many other layers. So that's the thing. It's a deep layered mechanism. And then we now are kind of very much looking into what is called as generative AI models. They are again same principle, ANN, artificial neural network, but they're designed slightly differently. And things like your chat GPT, which is again, it is actually a transformer. And then what transformers are, I'm just going to relate that to you later on in the discussion. But they are again nothing but artificial neural networks with some slight adjustments in the mechanism itself. We are also going to look at diffusion models, just briefly though, on conceptual level. And we are also going to look at convolutional neural networks, CNNs, which are actually widely used for image recognition and image processing. So with that view, we are kind of set on board to understand, by the way, a few more things that we need to understand before we move on to the next level. The thing that if you have not yet tinkered with any AI models, then you would probably not know. But essentially, what we are entering into, whether it's a neural network model or a decision tree, are just numbers. And these numbers are actually aligned to become a vector or matrices, as you may like to call it. And mathematically, they are getting represented in something, as all of us know, is a vector space. So it's purely a vector mathematics. And when you talk about NVIDIA and all other players who are doing so well, and when you say the AI chip and all that, all they're trying to do essentially is to enable this vector calculation, because that requires a huge kind of memory and configuration. So in ordinary case, CPUs are not built to handle those many parameters, like millions of parameters. Then what GPUs or NVIDIA kind of guys are doing, they're just laying out the foundation so that you can calculate and do things on those bases. So if you can do vector multiplication or addition, as we saw in the neural network, it's primarily adding and multiplying. Then, and if you are able to do let that machine do it for millions of parameters, then we can practically calculate everything that we need to. However, there's a limit. So beyond certain complexity, we can't. I mean, even for image processing, for example, these days, there's a limit. Image is simplified to make those calculations happen within the memory configurations. This all might change if there's a quantum compute that comes in next 20 years, but at present, these are the limits. So then now we have got enough building blocks to sort of define what AI is, and it's quite an open in the definition actually. And in reality, it's just a simple thing. It's just trying to mimic human intelligence. And all we are trying to do is uh, we're attempting to do that, but nothing has been successful so far as close as human intelligence. But there is a lot of, uh, let's say, good thing that is coming out of it. And all we are trying to do when we say artificial intelligence, we are only focused about learning. So a biointelligence, if you want to look into that way, has got multiple things. For example, biointelligence is also about evolution. Biointelligence, I mean, our genes actually are those mechanism which is doing that coding. We have those codes inside our body. So biointelligence is far more superior, and it's not just about only learning. There are lots of other aspects. There's aspect of evolution. So cell would like to survive. It would like to, do everything to survive, uh, whether we like it or not. And the way that has been so far developed our evolution as we as a being, as an intelligent being. In the AI world, we are only focused about learning, not the other aspects. So when we say machine learning, we mean that machines are learning like human beings. By the way, some of the other thoughts are also that we could be speaking about machine teaching. I mean, a teacher who's a machine who teaches a machine. So primarily, it's about learning, and the building blocks are the same that we discussed in these first three examples. It's either supervised or unsupervised learning, and there is also a random, it's not random actually, there's quite established concept of something called semi-supervised or self-supervised, but it's just to, you blend the unsupervised or supervised learning to make them look like it's semi-supervised or uh, sort of self-supervised. A question to everybody. When we say unsupervised or even self-supervised, do you think they can learn without human assistance in the AI world? Anybody? Any thoughts? So let me answer that because I think mostly you're in listening mode. So answer is they can't, and that's the whole point I want to drive here. AI machines are only as good as their training data, and unless and until you give them training data, whether it's supervised or unsupervised, they can't perform any further. So their world is just that. Okay. So then we look at these sort of generations of AI that has happened so far. By the way, AI that you see now is nothing new. I just want to let you know about it. This has already happened in 1980s. Most of the algorithms that even you see, this Gen AI and all that people are talking about, they already were pre-discovered mathematics. There's nothing new happening. Only thing that is happening these days is being able to, um, excuse me, I may have to go just for 2 precise minutes in the middle of this presentation, if you may forgive me from that. Allow me, because there's a very sort of a delivery that I need to attend to. Martin, may I take just a few minutes leave?
Okay. Quickly do what you need to do. Okay.
Thank you. I'm just going to turn off the camera, but I'm here, and I will be back in just 2 minutes. Thank you.
Let's get your feedback at the moment while he just takes that 2 minute break. Is this at the right sort of level for you, or is this too complex? At this point, please open your microphone and answer. Thank you.
Apologies, I'm back. Sorry, it wasn't the one that I was expecting. Thank you, everyone, for tolerating that. So, yeah, so when we look at, um, everyone can hear me, I hope. Yeah. So, when we look at these waves that AI has gone through, we've got wave one where we have got the expert systems that were discovered. By the way, this is the definition what DARPA follows. I think DARPA is something you are aware. DARPA is actually the premier institute which engages in high risk, sort of high reward research. I mean, the internet was possible because of these DARPA projects. So what they defined is that in wave one, expert systems came through. So everyone, so if there's an expert, say a doctor who thinks this is what needs to happen if there is a scenario like this, so that if then else case from that expert is jotted down, and then we created a system called expert system. So it was based on expert knowledge. Then wave two came, then lots of statistical models were engaged into this process. And that helped to, by the way, kind of get learning a little more forward with it. It can perceive, it can do some abstraction. Reasoning was available even in the expert knowledge areas. Reasoning, actually, as you can see, is quite high in the abstract sort of expert areas because it has those if then else blocks. So with statistical models, things started to become a bit more concrete, but it still had limitations because the number of parameters, I think everyone knows, is Statistics does not go beyond 3 or 4 parameters. If you give 10 high sort of parameter equations in a statistical bound system, it fails. It cannot cope with it. So, although this was doing fine, but then a new approach was required, then we got to wave three when you see all things like neural networks and all that came through. And that's where the perception part really got boosted up. I mean, if you see a robot, it can perceive quite well compared to a expert system. If you see other parts like learning, abstracting, and reasoning, they also got quite a boost. However, as I have mentioned, so contextual part is something we could capture. But however, as I mentioned, we are still limited by what we train. So none of these waves can break through that. So what's the future of AI? Well, people have defined it or coined it as AGI. AGI is where we actually look into that and say, okay, now the intelligence is such that whatever we do as human beings, our AI can do that as well. So we not only just learn from experience, humans do learn, and with training data, AI can learn too, but we extrapolate that and we actually form new sort of conclusions and new form of logic. That is what AI cannot do. And it's a huge sort of research area. And my gut feeling is it's very difficult to get into that. But nevertheless, this is the concept. Closer we can mimic your neural network, closer we might get. But there is something innate in human beings that enable us to do that. But then there's the concept out there. So you know the systems out there. So that's the future of AI. That's where we are going. So hope that gave you a very broad view and the founding blocks of AI, and then now we can move into various applications, and you would be able to follow them much better because it just got the foundation. Um, right. So at least may I know what kind of areas in everyday work that you use um, that you might have seen AI in real world. I mean, most likely Chat GPT, etc. So it would be great if you we are just I think 3 or 4 of us. If you may want to give me your experience on what sort of AI world you've experienced. Anyone?
Please interact.
Okay.
Don't, I'm just going to say some of you must be involved in business management or media or IT or, retail.
Okay. We will
Carry on,
we
Roy.
will delve into this anyway. If and most likely you would say, yeah, I know this already. But anyway, we are going to go through this to get a quick view of this. So, where you might have heard this year, particularly, there's a lot of talk about something called agentic AI just lifted off. So, where is it used and what exactly is this? Well, to be very honest, we'll look at a few of the examples here. Agentic AI is not new in the sense that it is more towards workflow management. It pre-existed in various formats. I mean, it pre-existed as isolated workflow management within applications like CRM or ERP. It also pre-existed with various programming blocks. But so most of the agentic AI that you would come across in today's world who tend to do some work for you are essentially workflow management tools, and they have wide range of permissions across the organization to log in by themselves and extract data and do something for you. So That being said, the true agentic AI is a bit different from what day-to-day life people would experience those AIs, so those agents. So in day-to-day sort of agentic AI, you would mostly experience a simple format where a workflow is managed. There's a if then else case, and that is what is getting executed. But in a very advanced form of agentic AI, you might look at a robot, and that robot might be able to carry out some sort of work for you, which will be based on concepts of things like reinforcement learning. Once again, this is not new, this existed for ages, but we are just sort of packaging it into one trend, commercial trend, to be more exact. So, what has happened because of agentic AI and because of the your chat GPT kind of chats, that now the same work that was possible earlier is getting done by systems, but they are getting those names and things like customer services. A, an agentic AI, can simply do that job, which a human used to do, like processing refunds or updating some sort of subscription tiers. And it can then upload and log into various systems, ERP and CRM, to reflect that. Similarly, something like sales pipeline can now also be supported by agentic AI. It can follow up a lead. It can shoot off some emails for you when the lead is out, when the lead is becoming very much interested from prospect to becoming a lead. I mean, the regular sales pipeline, you're all probably very much familiar with that. Then this agentic AI, instead of Microsoft Dynamics CRM, for instance, there's an agentic AI that will be able to interact with Dynamics CRM and do that kind of job that alternatively you have to do on a keyboard. So that's the kind of thing that it is doing. Similarly, in finance, insurance, and banking, it can do multiple things like identifying frauds, do some risk alerts, do some credit and loan underwriting cases. Once again, workflow that human can do, it is able to do as well. HR operations, it can onboard employees, it can send reminders, it can update holiday requests, things again, let's say junior HR executive was doing, instead of her, we would have agentic AI be able to do. IT operations, DevOps, they can deploy things in cloud, they can onboard people, or they can create provision things for employees or other, various options that they need to do every day basis. If the thing is more has got a pattern in it, they can utilize that agentic AI. So a quick question here. Does agentic AI work autonomously and it can just do its job independently, or it it is more efficient when you have got a human in the in the mix? What is your view here? Okay, my I'll give you what everyone sort of in the industry is aware, that agentic AI doesn't work of its own. It always needs a human in the chain. So although the number of human beings probably are going to be required less, but it still does need that. That's where it works best. It can't just do it everything autonomously of its own. There's a quick write-up here. You might look at it leisurely in your time. MIT, Sloan, their review in their magazine. I mean, this got published, I think, a few days ago. I thought it was best to get a quick view of that for you. So this is where all the various agentic AI models that is coming through, what they've researched, they have come through, they've just categorized them in sort of existing areas where things can be added. It could be a customer proxy, it could be a modular creator, or it could be used as an orchestrator. So have a read through. It's a very nice article to get a view how agentic AI is being used these days. Okay, so let's move into how does this agentic AI look like? And you might just be wondering, then what exactly is the difference between a GPT model like ChatGPT and an agentic AI? So this is just a very quick example here. I mean, if you scroll through, you might get various such examples. But what it is doing is, assume that you are an HR executive and you ask your company bot, so is Monday a holiday? This is just a fictitious example. Now, if Monday is a holiday or not is something that this chat GPT can go ahead and extract that data and say yes or no. In our case, it says no. And then the HR executives understands that if Monday is not a holiday, then they need to prepare certain things because some interns are coming. So to onboard them, and then multiple steps that this HR executive otherwise would have had to do by herself. For example, calling up IT, getting their laptops ready, getting their logins ready, ensuring they are in their Slack or company communication portal, ensuring they have got their teams, various logins, etc. So those bundle of actions that happens during onboarding that now can be taken over by an agentic AI model. So a simple instruction like prepare to onboard all new interns on Monday will get interpreted by will be taken over by agentic AI model. And then that agentic AI model is going to go ahead and do all those actions for you, and then it can come back and say, okay, 5 interns onboarded, and you might just ask again, give me details, and it will prepare a report for you, etc. So essentially, it has become a co-worker that you can rely on, uh, and then this co-worker, agentic AI. The difference between ChatGPT and agentic AI is that the the AI agents, they have ability to make decisions. They have ability to go through some memory systems. For example, they can go through the chat memory, which ChatGPT will not be able to do. They can ChatGPT will do some part of it, but not to analyze and make decisions on that basis. And then they can and these AI models, agentic AI models, can also look into the memory part, sorry, the knowledge part of it. They can derive or understand knowledge if it is presented in certain format. So the main difference between a agentic AI, AI agent, and ChatGPT model is that every AI agent will have goals and it can perform its task based on those goals. And the decisions that it needs to take are usually complex and they're multi-step. Whereas the generative AI ChatGPT model will not be doing all those things. Generative AI is all about generating something from pre-existing text or things like programming codes. So it just does that. Hope now it's kind of a bit clearer to you that difference that we have between ChatGPT and agentic AI. If you are, if you want me to explain any further, please do raise your hand or feel free to ask. Okay, let's move on. Just a quick snapshot of what agentic AI might look like in a low no-code environment. By the way, this is a screen grab. I haven't done it. I don't do this UI stuff. I do code. I develop through codes. But anyway, shout out to somebody in the YouTube. I'll leave that reference out. So essentially, it's a screenshot of what an AI agent may look like in the UI format of it. So as you can see, the agent itself, I'm not sure you can see my cursor. If you are able to see my cursor, then that's great. I'm going to be able to point out. Can you see my cursor or it's not visible to you? Okay.
Yes, I can see the cursor.
All right, thank you. So that is very helpful if you can see. So what we are doing is we are actually trying to create a user form here. And when this user form is submitted, let's say this is a new employee that you're onboarding, then AI agent has got various sort of hooks inside your organizational stuff. What it can do, it can go ahead and pull up a large language model like ChatGPT or Anthropic chat model. It can chat with you using that. It also has linkages to, we spoke about memory. So Postgres is just a database. It just keeps data, all your chat messages. So AI agent can read through that, which is difficult for generative AI to do all the time. And then AI agent can also go into your Microsoft Entra IDs, your entire cloud and your network intranet based IDs. So it can log in and do all stuff. And it can also go through the Jira software and do some things like enabling a Slack sort of channel or things like that. So what it does, it's a very simplified decision it is going to take. If this particular user is a manager, if it's a yes, then he gets to, create a channel. He can be an owner of a channel. If this person is not a manager, you just update that profile. And this is a very small workflow that is going to get executed on the basis of the chat you're doing. So this could be out of many level of actions, multi-action, that one of the actions could be doing just to check if the new employee is actually a manager, then you could take these steps. If not, then don't do. So this kind of code systems, this N8N is a German company who have developed this. But again, if you look at old school thoughts, I mean, this already pre-existed. I mean, this is nothing new. Every bit of this programming, it pre-existed, and the goals also pre-existed. I mean, learning pre-existed, but again, it got packaged as agentic AI. So let's enjoy it. Okay. So the next area we'll look at in something that mostly I'm sure every one of you have experienced. Whenever you go online, you shop something, there's always a recommendation that comes based on your what you've shopped, based on probably where you live, and based on your demographics. If you already have given your age or your gender and all those details, then definitely, I mean, if you've signed up for any loyalty card, I designed a loyalty card for one of the I mean, there's a Walmart who has got a subsidiary here, no longer subsidiary, but they are a primary retail organization. So if you do that loyalty thing, then all these things will happen behind the scenes. So what recommendation engine simply does is it picks up your various attributes and it personalizes the recommendation for you for kind of products you may like, kind of things you may want to do within a particular platform, or it could be a completely online platform. It could be part online, part offline platform. It could be just an app. So being able to look into this um, entire set of users and recommend something personal, that is feasible these days, and that's done through the recommendation engine model in AI. Again, we can go in the back-end discussion how they're done, but I'm going to just leave it at this point that they exist, and we can use it in retail and media sort of solution. I've given a quick example of that for you to have a quick go at it. You can check this site. It's a BBC site. So pretty much media probably is quite easier to understand. We can understand that quicker compared to an e-commerce site. They may have multiple categories. But here is a simple sort of article that has come through, and BBC wants to create this recommendation for its readers. And the way that it does is during training, this particular article is divided in body, headline, summary, and you can see something called tags. And there's a section based on these tags, which are the attributes that it's going to read upon. There's some business rules that's going to categorize it. And those tags might be, for example, it's a news about Malaysia. Then that tag would mean somebody who is living in Malaysia, would be more relevant for that person. So those kind of business rules are here, and then a deep neural network will be employed, which is just going to take inputs and give that output. And when it gives that output, there's a guy, I mean, usually junior uh, editorial executives sitting in that, I mean, not the chief editor, but people who work under him. And they would just look at that, whether that recommendation is really good or not during training when we are training that model. And then they will either approve or disapprove. We have got that example here. So if that particular recommendation has been, they have given just sort of for clue to the neural network what to do about it. So if it's unacceptable, then that learning was not right. Definitely need to change your weights inside this in that inside story, if you recall. And then if they are all good, satisfactory or appropriate, then no need to change those weights. So that's the kind of recommendation model that is used in e-com sites or publishing any sort of media site, including YouTube or any media site, not just article-based publishing. So that's one application. Then we move into healthcare. The reason I thought it would be good to sort of give you a quick view here, because we are going to look at lots of your AI-based applications, which you might have looked at in our discussion a little earlier ahead, or you would be looking at a few minutes down the line later in the discussion. So the kind of areas healthcare in itself is a world of its own. So it's really doing, I wouldn't say this one single slide would in any way be able to describe the depth in which AI can be utilized. But in this slide, I've just sort of highlighted few very um, let's say, key areas. But these key areas are not the only key areas. There's an extensive list. It's just for a quick overview. So what these machine learning models, and as we know, machine learning models are essentially deep learning neural networks these days, which are multiple layers of the network. I mean, there's a quick view of the sort of deep neural network here. These layers, when you talk about layers, they're just interconnected. When we say hidden, it doesn't mean really hidden. It just simply means the inside layers are not being utilized for input or output. That's all it is. But they are still being manipulated using those weights, and the neural network itself manipulates it the way it's been configured. So, so essentially using deep neural networks, and using some sort of machine learning algorithm behind it, we can look at images, we can look at various images, and as I said, um, convolutional neural network is the primary tool for going through image, scanned images, and making those uh, inferences out of it. So we can look at MRIs, we can look at CT scans, detect or X-rays, detect abnormalities, also predict trend. Things like things that wouldn't be possible, for example, for a human being to do all the time accurately. If there's enough training data, if there's enough scan images, you might be able to project what might happen likely in the future. So it's not just diagnosis, it's also predictive in nature. Drug discovery, huge. I mean, with various AI models, you can just simply reconfigure um, things that you want to do and then go ahead with that. By the way, thing that I've not mentioned here, but is absolutely an essential thing you might like to know. Biotechnology is synthetic biology is quite entirely dependent on um, utilizing these AI network circuit rules and building new organisms, either bacteria or yeast. But those organisms can effectively be utilized in various ways, including creating new drugs. So that's also another application. Uh, Medicine that is more effective for an individual based on their gene structure, again, could be an emerging area that we could look at. Robotic assisted surgery. This is where I love robots, but this is where I don't. personally, I will not make that choice. I want really a human doctor to do that live. I mean, not through sitting somewhere else, but people can. I mean, technically speaking, be sitting on Earth and doing a surgery in Mars. Actually, you have a good case. These guys came back from shuttle. So when they, of course, it's a bit far-fetched, but if they were robotic surgical machines in the space station ISS, then we could, a human surgeon sitting on Earth would be able to manipulate and be able to do that surgery. And while they do that surgery, then there are machine learning recommendations. For example, don't go too deep, or this is going wrong, or things like that. That can be given to surgeon. Wearables, huge market. I think that's the area that everybody understands as a huge thing in the future. And every now and then we all have those watches and all, but now it's also feasible to scan your brain while you're at home and be able to um, detect if something is going wrong. Right, so they were the sort of medical side of things, healthcare side of things. As I said, it's not exhaustive, but the list is just a quick illustrated one. So now we'll quickly look into, as we went past the applications and we spoke about Gen AI in our few slides ago. So when we talk about Gen AI, what they are, so this is just a very, very sort of simplistic view of what that is. So one of the things that I spoke about when we were speaking about the input data is everything that has to be input has to be a numeric vector. So a vector is simply not 3D vector, 2D vector. What I mean is it will have an x coordinate and a y coordinate. And in that x and y coordinate, you need to represent data. Right? That's the challenge. So when we talk about word, how do you think this could be represented? Yeah. It's out here in the picture, but if any of you would like to um, give me your point of view, looking at the graph. Eunice, you might want to give it a crack. Okay. So let me explain that to you,
A
guys.
nice day to
Um,
a nice
yeah,
a nice day to pick fruits, or do you want to buy some fruits, or do you want to go out cycling, or it's a good day for sports?
yeah, they are all valid thoughts. So thank you for your inputs. What we are looking here as, if you want to input words in a AI system, could be any, right? Could be a decision tree, could be a neural network, or could be anything else. You need to represent that as a numeric value, which will have sort of x and y coordinate. So what this is doing, it is actually, I think English has 65,000 words, probably. If I'm not mistaken, Martin has a better view on that. Um, so every single word that we know of, it is trying to give a numeric value to it. For example, these various kind of balls, volleyball or cricket ball or whatever they are, they're all given a value which is very close. For example, this value for x is equal to 1 and y is equal to 5. There's a ball here, whatever that ball is, I don't know. It probably is a tennis ball. Then probably this is a cricket ball, then that has got a value 6 as a y coordinate. So x is still 1 and that is 6. So what we are creating our own world of words, where words actually live in as a numeric value in a xy um, coordinate system. That's what we are doing. So there's a house, there's a castle, I don't know what this is a building, sort of, and there's a cycle. So all the words that are closely matched group can be grouped. They're given close sort of vector values. Those who are very diverse. I mean, a tennis ball and a building or a castle don't have any, they don't have any similarity. So they are sort of given values in a different way. So who gives these values? Anyone can. I mean, so that's what these large language models do. They give, first of all, values to words. They create a vector space out of it, and then they find out what really needs to happen. If you say something like sky is, and then dot 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 question, so you will get a response from your chat GPT that it is blue, because somewhere in this whole whole vector space, it is doing two things. First thing that it is doing, it is creating all the words which are similar, and the second thing that it is doing, it is trying to create a context out of it. So for example, um, all the large language models, by the way, when I say large language model or LLM, your ChatGPT is also an LLM. It's not beyond that. It is actually LLM. The only difference between so why LLMs came into existence, because you can ask them a specific question in natural language. If you go back to 1990s, not sure here anyone might be in that zone. I'm quite old. In 1990s, this was called NLP, natural language processing. But what is the difference between natural language processing and LLM is LLM is made up of huge number of processors, and that way we actually are able to uh, do large inferences. And LLP, the models were very small. I mean, if anybody recalls, DOS was only 360 KB, not 360, a little more than that, but the floppy size was 360 KB, whereas these are like in petabytes kind of data, and they have sucked in the entire internet into them, all the published material. So what LLMs are doing, they are reading those things, deriving a context, and then enabling us to generate new context. Not new, only from the trained data, whatever they can. So for that, they vectorize the words. They are called word embeddings. They tokenize. If you write a sentence, sky is, it will create two tokens, sky and is. And if you say, what is color of sky, then every word will get a token, and every word will then get a vector number. It will try to analyze. And the key thing that is different from a neural network to a neural network, which is a large language model, is that it remembers the context. Because if it doesn't remember context, it won't be able to make any sense of the sentence. So it needs to remember what has come through in the last, the last word and the next word, and the entire set of words within that sentence. That's why when large language models came first popped into the scene, they were designed using something called recurrent neural networks, which are neural networks with long short-term memories. So it's still the concept is same. You have memory somewhere where neural network is able to remember what is passed by, and then a language model can derive meaning out of a sentence. So just having a word or vocabulary won't do. And what we are doing now is we have replaced that with something called transformers. So transformers are again a neural network model which can remember the context. So that's what it is. It can remember the context, and all it does is it does it in a different way than these older things, and it can actually do it in parallel, which you cannot do here is scale up. So if it can do in parallel lots of things, you can scale up. So this came out as a Google paper. Actually, should have left a link here on that, called Neural Networks with Attention, and that keeping attention is something that helps you to derive that memory. And from that, it GPTs came up. So transformers, from transformers, GPTs are nothing but you have the entire sort of model being trained, and they're pre-trained on that transformer having massive data set. So that's what it is, right? So hope that demystifies what GPT is and how ChatGPT generates its various things, various sentences. Um, Having said that, we are just scratching the surface, not the foundational mathematical models, but an overview of what that is. Okay. So where we are now, we are still in the generative AI zone. Now we are looking at media and other areas which is using them for production. For example, I'm sure you might have heard about Google VO3 and things like that, where you can take the entry point of the VO3, and then you should be able to look at and generate various videos out of it. Even AI video filmmaking is a huge thing. Lots of people have started making at least short adverts using that. So you don't need a character, real life character anymore. You can have everything done through AI models. So how did it all begin? It began with few guys looking at it in UC Berkeley. I've left a link here for them, for you to refer it. So these guys, three of them, one of them is an Indian. I don't recall the name exactly, but these guys, they just what they did, they said, when you give an image as an input, we can go ahead and get an output, which is, let's say, if you give an image of a cat, you would get a AI machine or a neural network to say classify it as a cat. That's good. But how about we want to do it the reverse way? We say generate a cat, and it generates an image of a cat. And that is what these Gen AI machines are doing, but they are using a different model. They're no longer using the large language model kind of scenarios. They're using diffusion models. We'll get into that shortly. So essentially, if you input text, if you give a prompt, you will get a video. You can get that. You can describe a video, for example, create a 10-second video of a man walking on a mountain. It will generate something for you. Similarly, if you give a text for a melody to be created, it can create an audio melody. They are all transformer based, by the way. Transformer is the basis of it. So, as I mentioned, this happened earlier, and this is what they were doing. So, this is a paper, this is a link again from NVIDIA. You can go ahead and read that. How they are planning to sort of improve these diffusion models. So again, the concept, as I said, there will be a prompt. Suppose cat is sitting in the kitchen. So if you give that prompt, from this step, they are now generating, denoising everything to a cat. So what does AI models do? If you give them a picture of a cat, they will go this direction, in normal sense. They will go this direction. They will start to understand what that cat is and say this is a cat. But what they have done, they have just started to introduce some noise, more noise, and this is the final extremely noisy cat, which to human eye, we cannot see it any longer as a cat. But for a computer, because it acts on pixels, it can. So the idea is if this thing is fed, if the extremely noisy thing is fed, and it might be able to regenerate using a transformer model back to a cat, right? So at pixel level, there is still that detail available. Human eye level, well, no, but with that we can. And all we are saying, if we will start with a noisy image, and we will take a prompt which will come from LLM, like GPT, but from that prompt onwards, it will be the diffusion model which will generate that. So that is what is happening. This is much more depth. So in it, I mean, I would highly encourage you to go ahead and read that paper in your leisure time. Okay, so that was about the media side of things. Now we come to more of mobile and something active. Until now, the models are sitting in data centers and you're in your keyboard, and it's a bit, uh, let's say, unanimated. I mean, it is animated, it is exciting, but it's not, nothing is moving forward. So if we come to the realm of security and applications that AI applications around it, including space and autonomous vehicles. So the first thing that a robot or a drone or a satellite, or let's say any of the even the security cameras need to do is to be able to look at a scene or be able to look at a particular capture a particular frame, analyze that frame, and understand what's going on. All right. So vision is the first thing. So when we say vision, computer can have multiple vision. For example, we cannot um, see in the dark, right? But if you are going to be able to absorb infrared in your camera, then you can see from dark. I mean, even every single camera that we have, actually, if you have any old cameras and you can do an experiment, they actually come with an infrared um, filter, physical filter. So if you take that filter off, and if you want to go out, if you've got an old camera, you can experiment and go out in the night. You will see your images very pretty well up to a certain distance. So infrared lights enable that night vision. So what I'm trying to derive here is that vision is a broad spectrum. Vision is not just necessarily white light of the VB gear. You also have got infrared side, you also have got radio waves, right? So computer vision can capture all of them. They can sense it. And when they can sense it, then there are various applications that can be derived from it. So fixed camera applications for security and surveillance, we see it everywhere. Fixed camera for remote patient monitoring, that's also very important. And then we have drones for navigation. We see them, even if you get a consumer drone, not necessarily, let's say, military grade drone, a consumer drone can also navigate. They have some sense, not entirely, but they have some sense. Um, then EVs, everybody knows EV they can look at a road, detect an object, they'll not run over a person. It's collision avoidance and navigation. Robots, of course, we know that these vacuum cleaners everywhere, they go around, they clean, they can navigate themselves. And they can, things like your Amazon warehouse, for instance, they do these things automated, so robots can move. Satellites, of course, if you've got a even a good size, I mean medium sized satellite, you can track debris in the space. So there's a huge thing going on in space. There's a lot of debris issue that needs to be tracked, that so that debris don't collide. So that's also feasible by the same computer vision as an application. And my favorite, when you have robots, when they go out for exploration, like in Mars or someplace, they really have that vision. All they have got, they need to be able to explore. That's the most challenging part, right? Okay. So I have said to you earlier that we are going to look at this CNN at least at a conceptual view. And I told you that CNN is the fundamental building block for image recognition and anything to do with computers, with images. So that's what we are looking at here again. So we have got, let's say this is zebra. And when you input that zebra in all this artificial neural network, how do you think this actually identifies this as a zebra, not as let's say, elephant or anything else, or a dinosaur? So it does so because just like human eye, it actually sort of captures blocks, which are very small sort of pixels from a frame. And it then creates layers of those pixels. It has an internal mechanism. And it tries to identify what is in this small area of pixel. So what is that it knows something that it knows that is very similar, because of training data. What is this thing? So it understands this is a part of a zebra. So these individual layers are fed into your artificial neural network. Every of them, they go in. And then when they go in, these layers are kind of sliding. I mean, each particular frame is scanned with the small features that it has identified, and it tries to look for something that it has in its database. So is it, just to simplify it, is it a nose of a zebra, or is it a trunk of an elephant? It would know from its database of those small things. So these individual small, things that you see here as blur, they are getting matched by these features inside this neural network, and then we essentially arrive at the conclusion of it. So the how part of it is quite interesting. We can always look at that at a later discussion. But overall, this is how convolutional neural networks work. They work on the sliding part of deciding feature by feature individually inside each frame. Okay. So any thoughts here for from anybody about the visual recognition and you know for applications that we spoke about? Great. I would be available to discuss even later. So let's move forward. Um, Great. So then now we are looking at the same sort of extension of the same thing, but once you've got a vision, you obviously want to move, because if you don't move as a robot or as an EV, then, I mean, there's no purpose, right? So the movement part comes for what in robotics, we call it autonomous navigation. And but it's not, again, purely autonomous. I mean, it's based on some algorithms which are, again, trained. So it's not like human autonomous being, but within the fair boundaries of what training data it receives, it can do some action. So the primary thing that it actually looks at is there are two things that, um, let me ask you a question. So how do you know, for example, you've reached your house? Just as a quick question. I mean, I think anyone can answer that. Anybody want to take that up? So how do you don't enter into anybody else's house? I mean,
You recognise the front door.
that's right. You recognize your front door. You also recognize where you are, isn't it? So in your mind, you've got a map. You've got a map which you know what that is. So that map, you relate to your location. I'll tell you a funny example, in the sense, as a fictitious example. If actually all that we experience in life, we think it's physical, but in reality, it's all experienced in brain. Technically speaking, if your brain is alive, you are still alive, even if you're not physically have got anything else to experience. So if these experiences can be input in brain, you can experience that. So everything that you're experiencing only because you're able to correlate your location with a map. That's how you are experiencing that physical world. So the reason I gave this example, because for robot also, although it has this sensory mechanism of movement and sensing through computer vision, etc., and it has a locomotion through things that it does, wheels or various things, but it actually everything is inside its brain, and that's the brain that we are programming. So we have to think on that basis. So when we are looking at perception of a robot and we wanted to navigate, it should have a map. And that is why these two questions are fundamental. So robot should know, if it questions itself, where am I? And then it should have a map. And based on the map, it can figure out. So if it will look on the left side, what's on, it sees a river. On the right side, it sees a mountain. And it has a map inside already. Then it knows, okay, I might be probably here in between that particular, any sort of location, let's say Mars, a certain valley. Either that should be available, or if it doesn't have map, it can create a map. It has that ability. But to do that, it should know its location. So it should know for sure where exactly is it, situated. Where is it starting from? So if you don't give that robot where that location is, it won't be able to draw that map, because think about it. You say you entered your house because you know your front door, you recognize that. But what if you don't know if really that is your door? I mean, they're all similar doors. Just as a fictitious example, let's say every single house looks identical and have identical doors. Everything is identical. So you would not, in that scenario, be very easily able to identify where are you. Are you standing in front of your house, or are you standing in front of neighbor's house, etc. So location, if you don't have got that, then creating a map mentally is difficult. So ever since we have wanted as a human being, when we have become intelligent, we either can have a location or a map. But one key factor that also robots are adopting now, we are able to do them, both of them simultaneously. So I'll go into that point just shortly. So what EV does, EV has got the easiest job. This Elon Musk stuff, the guys, it is the brain dead job. What I mean, the EVs already got GPS, they got a map. They just know where they are. EVs don't have any, sort of uncertainty about where they are or things like that. They don't have to calculate anything. So they just know where they are, and they just need to navigate. So they have a location already in them, they have a map, and they can go ahead and navigate, or any place they like. But when you talk about space robots, say a robot has just landed in Mars, then it might not have a location exact, and it might not even carry a map. Although, technically speaking, map is fed, but just imagine a scenario when it doesn't have, I mean, standing in front of all the mountains that look exactly the same, right? Something like that. So the way to solve that is to simultaneously attempt to create a map, and to be able to, when you mentally, in the sense, inside the robots, circuits and brain algorithms, and simultaneously map them. Sorry, locate yourself. Try to locate. Try. The word try is the right thing. So you will have a probability where you are. You are not sure as a robot what it is. So this SLAM thing is quite important and significant. So you do it in small bits. You think that's where you are, and you draw a small part of the map, and you keep navigating the region, keep, drawing the map. And when the robot or the algorithm is able to do a complete loop of a circle, it then can correct itself some of the bits, the errors that might have happened inside in the map and the location. And that way, it can generate it simultaneously. So closing the loop is very important. If it can't close that loop, then its map and location might not be 100% accurate. So that's how robots work. That's how the space and EV sort of applications way happen. So that's there. So we've come to the end of our presentation, and we are here just doing a quick recap. Throughout this presentation, first we went into understanding and creating the building blocks of what AI is. You have sort of have got a fair bit of idea now that AI building blocks are made up of various models. They could be supervised or unsupervised learning. The thing that is taken off and mostly people are going gaga about is neural networks. which is, by the way, supervised learning. And then based on that, the various application areas that we have looked at business management, and we saw a workflow automation, which is taken care of by agentic AI, which can make decisions. We also looked at various media and IT sector examples like generating codes or generating, media stuff, text, video, audio. That is now these days done by generative AI models. Behind the scene is a transformer. Behind that transformer is still your good old artificial neural network. Healthcare examples we touched upon. Diagnosis is just a sort of a key phrase here, but we touched upon so many areas. And all those are done by deep learning networks and machine learning. We spoke about automotive sector, we spoke about security and space, and we derived on the various applications through computer vision and autonomous navigation to enable these sort of sectors. And we saw behind these things that looks quite wonderful, behind that, for image recognition and anything to do with computer vision, you have a CNN model. For autonomous navigation, you would have some sort of SLAM model behind the scenes working through it. So that's the gist of it. All the AI applications we looked at. I've given you the crux of it. Try to demystify. So, and there are many other terms you might have heard, but they more or less fall within these categories. So that brings us to the close of the presentation, and I'm ready to take any questions you may have. Actually, I'm going to leave this slide here just in case you want, or if you want me to go back to any other slide, please just let me know. And very happy to take any questions that you have.
Roy, thank you very, very much. That was quite intriguing. I'm, not deeply involved in that world, and I've certainly learned a few things from it, which I'll be stealing and using in presentations myself.
Absolutely.
When I talk to other people. But thank you very much. Any of you guys got any questions? I know we've gone well over the hour, but I don't care about that because for those of you who are deeply interested, and there are some of you there who are deeply interested, I wanted you to get the whole thing. Here's your chance to say thank you to Dr. Roy, and here's your chance also to ask some questions. Okay, I think maybe what's happened is we've got a few people still online, but they've sort of moved on to other things. Thank you very much, Roy.
Thanks. Yeah.
Great thing. One of the things you might want to know is that you have been live streamed on YouTube as well, and we have picked up.
Oh, really? Oh, wow.
We have picked up some YouTube viewers as well. I think Yanis is here to say something. Yanis.
Just see simple question, which I was
Sure.
still wondering the answer for spherical on the left. The other one is on the right. If neither one, what was the answer just now, Dr. Roy?
Yeah. So let me go back to the slide and
Yeah.
why we actually.
I mean, this is just out of curiosity,
originally.
nothing. Yeah, this is nothing.
Yes, absolutely. Why we actually moved into that? It's a very good question. Let me take you there. Sorry, it's actually different. We had some scenarios here. So why I took this example, I created this example. We were looking at something called clustering. So when you look at this slide, right, you see this is called, these are clusters. So these clusters is what I was trying to project towards when you're looking at unsupervised learning. So we took two examples. One was that example of having a kind of wear and diapers, which falls under this association rule. And the other one is about clustering. So instead of a robot, you have got here the AI algorithm. There are a few different types of clustering algorithms, but most famously, K-means clustering is an algorithm which runs when you give it some sort of, let's say instead of spherical balls and square boxes, we give this articles, and these articles are about a particular topic. Let's say the topics are, just for sake of discussion, some topics relate to the UK, some topics relate to Malaysia, some topics relate to global sort of context. So what will happen is these clusters are going to be formed after running that algorithm for a few iterations. So k is actually the number of times you run it. So if k is 2, you run it twice, 3. So essentially, if those articles are given a vector representation, after some time we will see centroids, and these center of gravity, let's say, which will say this green dot is, let's say, the UK, and all the articles that are about UK in your vector representation are closer to me. So I would say this cluster is UK, but it doesn't know it's called UK or Malaysia or anything like that. It just knows that in the vector space, what is more similar and closer, it draws them together. So that's the clustering. So robot was clustering. When you were training that robot was clustering, putting balls in one place and the box in another. Similarly, anything that is similar gets clustered in unsupervised learning, because unsupervised learning is, the other word of unsupervised learning is unlabeled learning. So it was not labeled. So when you are feeding in training data, you're still feeding in training data, right? I mean, it's not without training data. The training data doesn't have a label. So you recall that in artificial neural network, we said every training data we actually give, it gets at the end labeled by the human being, saying that, is it right? Is it wrong? And then it floats through back propagation, trying to correct its weights. And there's a bias as well that it corrects. Whereas in the clustering, we don't give any labels. We just give them data, and based on these iterations, it is going to form those clusters. So it's a kind of learning process based on the data, but it is not supervised, and that's the key distinction. So based on our scenarios, as we took over, as we discussed those first three scenarios, it pretty much gives you the solid foundation that you want to think about for unsupervised learning and also supervised learning. So, Yunus, does that give you?
Makes sense. Makes sense. Yeah. Thank you so much. Yeah.
Sure.
Thank you. Yeah.
Okay, everyone, thank you very much. We have to close this down. We've gone well over the 1 hour we were meant to do, but it is an incredibly interesting and intriguing subject area. Dr. Roy is someone who we can reach out to. If you want to talk to him directly, please contact me, and I'm happy to act as a conduit. Thank you very much, everyone, for taking time to be here.
Thank you, Dr.
An incredibly interesting talk. Thank you very much.
Thank you for this opportunity.
Thank you, sir. Thank you, doctor. Thank you.
You take care. All right. Thank you. Bye.